Okay, make sure this is on too. Move this, it's like right in my face. Get it kind of lower. Okay. Cool. All right, everyone. So, and just regarding the quiz, this is the first quiz of the class. It's, basically I'm trying to figure out exactly how to write these. I might grade this one on a curve. I might make adjustments to how the quizzes are created in the future as well, based on how this went. So do bear with me. My goal is for my mistakes to not impact your grade, because that's not terribly fair. So, yeah, basically if there's something where one of the questions was completely unclear and everyone got it wrong in the exact same way, that tells me that something about the question was wrong, not you guys. So, yeah, we'll figure that out. If you weren't here last class or just joined and therefore also weren't here last class, who leaves a marker? Savages. Close the markers. Look at this. There's another one. Ridiculous. They're all dry now. I don't know why I bother. Anyway. Oh, did I? No, I didn't. Okay. Distracted myself with those markers. Apologies. So, yes. If you weren't here last class, or if you just joined the course, don't worry too much about the quiz. There will be a makeup quiz for folks who missed it next week during office hours. It will be slightly different from this quiz, but it will cover the same material. Okay. Before we start with the lecture, are there any questions anyone has about the course structure, the quiz, or anything like that? Awesome. Cool. All right, so today we're going to be talking about functions and closures in Swift. You will probably be familiar with functions from other programming languages. Closures is a word that you might not have heard before. You might have. It depends on the language. A lot of languages have a very similar idea with a different name. So don't worry about it too much. We'll cover that. And this doesn't work. Of course. My clicker is not working. Give me one moment to try and debug this. Unplug it, replug it. There we go. Okay. I needed to get into it with focus. All right, so before we talk about functions, we need to talk about scope. This is also something you'll probably be familiar with in other programming languages, so we're going to go over it very quickly. So, what is scope in memes? Scope is a Russian nesting doll. It's very full of itself. You can have scope within scope within scope within scope. It is recursion, but not really. Don't believe me when I say that. It's a lie. But I thought it was funny, so I included it. And it's also kittens in a box. Basically, when you put stuff in scope, it's all in that same scope together, like these kittens. They're also very cute, and they're yawning. So what is scope, seriously, in theory? Scope defines what memory data that is stored in your active memory your current executing code can access. When code is grouped together in a file or in a function or any other way, those pieces of code share scope. They are within the same scope. If a variable is grouped in scope, that means it is accessible. So variables and constants in Swift, if it is within the same scope as the current code that is executing, you can access that variable or constant. Scope can be nested, as I mentioned on the meme page. You can have scope within scope within scope. If you have a variable in an outer layer of scope, it can fall in to an inner layer of scope. Essentially, any variables or functions or whatever that are declared or defined in a scope outside of your current scope can typically be accessed from within your scope, assuming it happens in the correct order. Variables can also fall out of scope once your scope completes. The end of a function, actually that's primarily at the end of a file, I suppose. At that point in time, the variable tends to go out of memory and gets marked for cleanup. Not always, but sometimes, most of the time. And then the highest level of scope, the furthest high up you can go, is global scope. That's also the most dangerous level because you can access it from literally anywhere in your code. So that's all theory stuff. What are we talking about in practice? What is this actually? It's brackets. Really, mostly just brackets. Brackets tell us what our scope is. If you ever see brackets, those are defining scope. Indentations can help us visualize the scope, but in Swift, they are not required. In languages like Python, you use indentations instead of brackets, I believe. There are a number of languages that do it all in different ways, but I'm teaching Swift. Whoop, this guy went flying. One sec, there we go. Losing my mic. I'm just gonna hold this thing if it doesn't work right. Please, just stay on, for the love of. It's like built for ears that are 10 times larger than mine. I'm teaching Swift, so I'm telling you how it is in Swift. And then sometimes people will call this context instead of scope. So they say, oh, within the context, right? If it's in the correct context. Context is one of those words that gets used a lot in programming, and it means a lot of different things to a lot of different people in a lot of different languages. Don't worry about it too much. Feel free to use it for anything. You'll probably be correct in some way. So I prefer to use the word scope because it's a little more specific. Okay, so let's look at some code. So here we have a variable that we define within an if block. This block has brackets around it. That tells us that that is defining an area of scope. Okay? So we define a variable within that scope. However, we get an error when we try to use that variable outside of the scope. Scope is defined by the brackets outside of the scope, but after the variable has been defined, we can't access it because we are outside of the scope. It's fallen out of scope. In this case, message doesn't exist anymore. It's been cleared from your local memory. When you are within those brackets, though, message is in scope. So if we pull in print message, then we are now in the same scope as where message was defined, and we can access it, right? On the outside, we have an even higher level of scope. If this is just your standard script file running this, nothing else around it, then we're talking about global scope on the outside, okay? But if this is, say, in a function or a method or somewhere else within another scope, then the outer scope would be not global scope. Global scope is the highest you can go. So, as I mentioned before, if you define a variable or a constant outside of the scope, and then you try to use it inside of the scope, you will be able to, assuming that you do it in the correct execution order. Obviously, if we declared count after the if, it would be very confused. Okay. So, in Xcode, there is a very cool feature that you can turn on if it's not default, but I think it is turned on by default. I tend to turn it off, but it is there and available for you. It is called code folding. And essentially, if you're in a playground right now, you can mess with this. If you create an if statement or a function or anything, basically anything with brackets, and you see this little kind of gray box here to the left, if you hover over it, it will show you the brackets enclosing that current scope. And if you click it, it will condense it all down. And you can look at everything as if that scope didn't exist. Okay. Now that we've talked about scope, let's talk about functions. So functions in theory are reusable blocks of code. They are a black box that receive a set of inputs and typically return a single output. They accept for their input things called parameters. For their output, they provide what's called a return. Like variables, functions can be called within the scope that they are defined in, as we were seeing with the definition of the count variable and the message variable. Those rules apply to function definitions as well. So what is a function in practice? In practice, it is a definition for the function and the block of code that you want to execute when you call that definition. The definition includes an identifier, also known as a name, for those who prefer to just use natural language rather than specific computer science theory language, parameters, and a return type, which matches pretty closely with what we were talking about in the theory slide. So the only other thing to note is that when you are defining functions, in order to make sure that they are unique and different from each other, the compiler cares about the whole definition. So the identifier, the name, the parameter list, and the return type. So you can have a function with the same identifier, but if the parameters in the return are different, or just the parameters or just the return, actually just the return might not work, but essentially, yeah. You can have functions with the same name that behave differently. So when do we want to create a function? Functions are used when you don't want to write the same code a second time. If you find that you are writing something that you've already written before, consider putting it in a function instead. If you have a piece of code that you want to behave differently based on input, if you want different flows of logic, if you want to be able to do things differently, but you want it to be kind of contained within itself and then give back a value, that's when you use a function. And they are also frequently used if you want to change or calculate something in a way that you expect would be reusable, which gets back to the first point, which is the primary reason you ever use a function. So let's talk about defining and calling functions. This is a function definition. This is how we define and create a function in Swift. It will look somewhat familiar to you if you're familiar with, other languages, but it looks a little different as well. So we're going to go through it. So to start with, we have our declaration keyword. Much like let and var for constants and variables, we have to tell the compiler at the very start of the line, hey, this is going to be a function following, okay? Next up is a function. Then we have the identifier, also known as the name. This is the way that you're going to call the function later on. Then we have our parameters. Weird. A return indicator, and our return type. So the parameters are your inputs to the function. They are the things that you want to be able to pass to the function so that it can then perform some operation. The return indicator is just kind of a placeholder thing that's intended to tell the compiler, hey, what's coming next? We're done with the parameters. Now we're going to show you the return type. And then the return type is the type that you return from the function, okay? Because Swift is a statically typed language with very little type coercion, your return type is very important. If you don't have a return type, though, if your function is something that just prints a bunch of stuff or makes performs a mutation, changes some things, but doesn't actually give anything back, then it has what's called the void return type, but really what that just means is that you're not returning something, so you don't have to worry about it. In order to, indicate that, you don't have to do the dash greater than void. You don't have to use the return indicator with void. You can just leave it off. So after you define the function, then you have the body. So the body starts with a bracket and ends with another bracket, just like an if or a switch or a for loop or whatever, right? This is also tying together with the scope. Your function has a scope, and it is defined by the brackets around it. And then you have your function body. In this case, we have a few lines of code that are taking in two int values, turning them into doubles, performing division, and then returning those doubles. Or returning that divided double, or the quotient, if you will, okay? So, of note, while we're within here, we are accessing the different parameters and using them in these lines of code as if they were constants that were defined previously, okay? And it's worth noting that in Swift, parameters are constants, okay? So you can't modify them. Once they're passed in, they're locked into the state that they are when you get them. You can copy them somewhere and then modify that if you want, but LHS can't be changed. Same with RHS. The other thing to note here is that the return keyword is what's used to give the promised return type for the function. The promised return type is, of course, the return type after the return indicator. And here we have a double dividing by a double, which results in a double. Therefore, our return type matches with the code that we are putting after the return. Sometimes you'll want to just return a single variable. Sometimes you'll use an expression like this that does evaluate to the correct type. It's all to flavor and taste and personal preference. So let's look at how we call functions with Swift. In Swift, you call a function by typing out the identifier, open parentheses, the parameter name, colon, the parameter value that you want to pass in, and then, continue on with all further parameters with commas in between, and then close with a close parentheses. One thing to note is that, especially if your function is on the right-hand side of an assignment operator, the constant or variable you are assigning to must be of the same type as the return type of your function. The identifier matches, your parameters match. Of note, when you're calling a function, this is going to come up in the next set of slides, we'd call this the argument label rather than the parameter name, and that's a Swift thing, and that has to do with kind of what's coming up next, which is being able to define custom argument labels that are separate from your parameter name. But for now, just know that it's an argument label. Your values also need to match your type, so you cannot pass an incorrect type. Because Swift barely does any type coercion, you can't try and pass a double where an int would go. It won't work. You have to cast it. And now we'll talk about those argument labels I was mentioning. So here we define the parameter for a function. By default, if you do not change anything about how you define functions in Swift, your parameter name is your argument label. It is the default argument label if you don't give it any further instruction. However, you can provide a custom argument label. It looks a little weird, especially if you're used to like Java. But what this allows you to do is when you call the function, instead of using the parameter name as your argument label, you can use the argument label that you've provided. So, for example, here we've made this change. Now we get a compiler error where it says that the labels are incorrect. Right now we're using the labels LHS and RHS. However, we have set the labels by lieu of the fact that we've put them in the definition in the way that we have, int1 and int2. Those are the expected labels. So in order to get rid of this error, we just change those to int1 and int2, and the error goes away. So if you want, you can also omit argument labels and just call a function like you do in every other language. This is not the default behavior in Swift. Most languages make this the default behavior. That's not the default behavior in Swift. In Swift, by default, your parameter name becomes your argument label. But if you want to just, pass in a value and not have an argument label, then you just put an underscore where you would put an argument label. Okay? Doing so will, in this case, throw an error because there is an argument label where it's not expecting one. Get rid of the argument label, error goes away. Now you've just passed in just the value that you want to go into the function. You can also, in Swift, provide what's called default parameters, okay? A lot of languages also do this, so it shouldn't be too new for you. Basically, define your parameter exactly as you would normally with an optional argument label, your parameter name, the type, and then do an assignment as if you were creating a constant or variable. Do that all within the same block and then put a comma after it if you need more. So now, when we call divide numbers, which is now, by the way, a useless function because we're always returning the number that's passed in, but don't worry about that too much. If we only pass in one number, that is to say. So if we call divide numbers 10, then it will return the value 10 because it has the default value for the right-hand side argument or parameter. So when can we call functions? When are they available for us to call? They are available when they are in scope, just like variables. So if it's in the same scope, if it is defined in an outer scope before our current execution block, or in the global scope, and they can be called from anywhere when they're in global scope. A great example of a global scope function is print. This is a function that you've seen used here in these lecture slides and also in the quiz a number of times. And that is a great example of a global function. And so we're going to go ahead and look at it. And I messed up my animations here, so you get to know the answer before I show the question. Don't worry about it too much. This is the exact function definition for the print function in the Swift Foundation library. So this is exactly how it is created by the people who build Swift. All right? So you'll recognize a lot of stuff in here that we talked about. This has multiple parameters separated by commas. It has default parameters using these assignment operators. It has omitted argument labels, such as items. The parameter items has an omitted argument label, meaning that when you call print, you don't need to provide an argument label for that first parameter, right? It also has something new, this any ... Don't worry too much about any. It's just another type. It's a special type. It's a type you should never use if you can avoid it. So don't worry too much about it. But the ... is the new thing, which is a variadic parameter. So a variadic parameter indicates that once you're within the function, that parameter is an array of whatever the type is before your ... that you put, right? So you put a type, and you put ... And then within the function, you can treat that parameter as an array. Outside the function, when you call it, instead of passing in an array there, you pass in individual numbers. Click. Click. There we go. So, for example, here we have a function that counts the number of ints passed in. So we omit the parameter name just because, or the argument label just because, we want to. And then we have our variadic type for the parameter. We do our thing where we basically just, increment our counter, return it for each number that is in numbers. So basically it just counts how many parameters get passed in. And then when we call the function, we, instead of passing in an array of numbers, or of ints, apologies, we pass in as many ints individually as we want, separated by commas, as if they were unique individual parameters. But they are not. They are one single variadic parameter. That's why print works pretty well, typically, because you can kind of pass it sort of any number of strings, and it'll, handle it okay. All right, so that was function definitions. Next, let's talk about function types. Oh, this was supposed to come in one at a time. Well, don't worry about it. All right, so in Swift, function definitions are a type, like int or double or float or array or whatever, okay? You can store a function, because of this, you can store a function in a variable or a constant and then use it again later from that variable or constant. So let's show you how you would store a function. Here we have our divide numbers function that we were previously looking at. We define a constant called division. We use the assignment operator, and we just use the function identifier. It's important that you only use the function identifier for function assignment, just because if you try and if you call the function there, then instead it's going to try and take the return type and put that into your constant, right? And so if you were to say, open parentheses and then pass in some numbers and stuff, it'll do the calculation, it'll return the double, and then division will have a type of double, because Swift does infer types if you don't provide an explicit type, because it needs every single constant variable to always have a type. So later, with our now function constant, we can call the function as if we were using a new identifier for it. It's almost like a form of aliasing. There's better ways to use this, and we'll be getting into those shortly. But for now, essentially, if you store a function into a variable or a constant, then you can call it as if it was the function itself. So when you are typing out division in Xcode, you will get a pop-up like this. This is your kind of autocomplete thing. I think it's called something different in Xcode. Visual Studio calls it IntelliSense. I think JetBrains just calls it autocomplete. They all call it something different, proprietary. But the important thing here is it tells you a lot of information about the type of whatever variable or constant you are referring to or you are typing out, right? So as you type out division in your, Playground or Xcode file, it will show you this information. This is your type information for your function, or in this case, your variable that is storing a function. So it's telling you what type this is, okay? So for now, don't worry about this @sendable thing. We will cover that when we get into concurrency in class, I think 5, something like that. That's new. It's a Swift 6 thing, kind of. It used to be an optional thing in Swift 5.9, and now it's a required thing in Swift 6 that you'll have to worry about, but we'll cover that when we get to it. For now, you can ignore it. So this is our function type. So this is the structure for when you are creating a type for a function, right? It is a compound type. It consists of other types, like a tuple, which you would potentially remember from the reading. So a tuple looks actually kind of a lot like the left-hand side of this, but because we have a right-hand side and a function type identifier or indicator, this is a function type and not a tuple. So here we have on the left-hand side the parameter type definition. This tells us, okay, so this function has a type, this type of function or whatever. Functions of this type, generally speaking, take in two parameters, one int and then another int. This is the return type definition. Functions of this type take in two parameters, an int, and return a double. And all in all, together, they are a function type. So, when can we use function types? We can use them as variables and constants. So you can use them to define, hey, I'd like to have a variable or a constant that has a function type. That means that moving forward, the only things you're allowed to assign to it are functions that have that type. Functions that have that type are functions that take in two ints and return one double. You can also use it as parameters in other functions. I heard you liked having functions in your functions, so we gave you more functions to put in your functions. Something like that. So, again, you can pretty much use these just like you would any other type anywhere. So, for a parameter, here, valid input given function takes in an operation parameter, and that parameter needs to be a function that has the type, takes two ints, gives one double. We can also use them as return types. So, in this case, this function would return another function that you can then call and use later on. And that pattern, where you have a function that creates a new function, is called a factory. And we'll get into that a lot more later when we talk about patterns and stuff. But for now, know that you can create brand new functions and return them within one function. But the best way to do that is using something called closures. So closures, in theory, are an anonymous function. They are a block. They are a lambda. They are a lot of names for the same concept in different languages, so you might be familiar with them from that. It is a portable function that is intended to be passed between scopes, which is a true statement in Swift 5.9 and a semi-true statement in Swift 6 due to that @sendable thing I told you not to worry about, and we'll cover that when we get to concurrency. It is a function that can specifically capture variables from the scope that it is defined in. This is very, very important, and why closures are so helpful. Closures can, if a variable or a constant in an outer scope falls into the scope of a closure, and then you leave that scope, not the closure's scope, but that outer scope, whatever it was, let's say another function. That closure still has access to that variable or constant that fell into it. If you try and use it, it's captured and it's held in memory, even though it would have already fallen out of scope naturally. And we'll look at some examples for that in a bit. And then they are nested functions, and global functions are special kinds of closures. They are special cases of closures. So if you put a function inside of a function, that's technically a closure. It's a closure with an identifier rather than being anonymous and not having an identifier. But it's still it's a kind of closure. Same thing with global functions. They're special. But for you using it, all you need to know is that a closure is a function and a function is a closure, and they behave a little bit differently, but it's not a big deal. So a closure in practice is usually put into a variable or a constant with a function type. So the variable or constant has a function type, and you assign a closure to it. It is very frequently used for callbacks, so that you can, in a much deeper nested scope, inform a much higher level scope that you are, don't have direct access to. Hey, by the way, this thing happened, something occurred, right? Something's done, here, have this value. It is also a way to implement what's called the delegate pattern and protect against something called retained cycles. We'll cover those when we go over automatic reference counting. I think that's next class. So don't worry about it too much for now, but sneak preview. All right, so let's look at how we define a closure expression. This is a closure expression. It looks kind of like a function, but a little bit different. So when we're first starting to define a closure expression, we open with a brace rather than something like the func keyword. Then after the brace, where we're saying, hey, we've got this scope that we're about to create, we define our closure type, okay? So we basically say, hey, this closure is a function that has this function type. You'll note that because we're about to use this closure, because we're about to define the body of the closure right after this, this isn't just a function type, it's a closure type because it also has parameter names. And the rules for this apply the same as they did for function definitions. You can omit argument labels, you can set defaults, variadics, etc. Then after that, we use this in keyword. It's weird, it's different, it's unique, it makes Swift quirky. I'm not entirely sure. I think it's because the bracket has already happened, and so we don't have another way to say, okay, cool, the definition's done, now time to start actually using the code. But basically the in indicates the end of our closure definition and the start of our closure's body, the code that's actually going to execute within the closure. So, one of the things that Swift can do is infer the type from context. So it is a statically typed language that doesn't have coercion. However, it's very, very good as a result at inference. It's very good at figuring out, oh, I see, you mean that this closure is expected to be this. It needs to be this type. If all these other things that I've seen, if the compiler says all these other things I've seen in the code are already true, which they are because I've compiled them and they compiled, then this line means, like in this line, this closure has to have this function type. So you can take a bunch of shortcuts as a result and don't have to provide an entire closure definition. And in fact, people rarely ever do. So to start with, let's say that we define the function type for our constant, as we've been talking about here. And we say, yeah, this constant can only ever have a function of this type stored. Now, Swift has a clue whenever we're trying to assign a closure to this, right? You can also note that while this is a constant, because we haven't technically set something for it yet, we can set something later. Basically, what Swift is doing is kind of removing multiplication and putting this whole equals thing after this. Like it does that in the compiler. You don't have to worry about it too much. Right. So we have some clues now that allow us to take some shortcuts. So first of all, we do not have to provide all of that information in the function definition. It knows that this closure will return a double. We don't need to tell it that. It knows that this closure takes in two strings. We don't need to tell it that. The only thing that's missing are the parameter names or the argument labels. No, sorry, parameter names, not argument labels, because you don't call this explicitly. So these parameter names have to be defined for our particular creation, our particular closure that we are creating. So in this case, we'll use LHS and RHS for left-hand side and right-hand side. We're going to perform multiplication. So we're bringing in two strings. We're going to cast them into doubles, and then we're going to multiply those doubles and return the result. If you are attempting to put this into a playground right now, you will find that there are errors, and those occur when you do double.init LHS and double.init RHS. It will tell you that LHS double and RHS double need to be like they're optional types. We'll talk about optionals in the last portion of the lecture today. So, Don't worry about it for now. Yep. So another thing we can do is have an implicit return. In a closure, if your closure is a single expression rather than a series of statements, it assumes that that expression evaluates to what you want it to return. So in this case, and here we can go back, we're returning LHS double times RHS double, right? However, if rather than assigning these to constants, we just do the multiplication kind of inline all at once, we don't need a return keyword. It knows that this is a return. This only works if it is a single expression. If you ever add anything else to it, an if statement, a switch, another variable or constant definition, then you need to use a return keyword. I thought there was one more. Oh well. Okay, so next up we're going to look at function types with no parameters. Sometimes your function, as we talked about before, will not return something. It'll return void, right? Sometimes it doesn't take in parameters. When we're looking at a closure here, we have our parameters, we have our return, but how do we tell it, hey, we're not returning something from this closure, or hey, this closure doesn't have any inputs, or both of those things? So that's what function types with no parameters are. So here we have a function type that we define. We have an open parentheses and a closed parentheses. Oop, sorry, pre-clicked. My bad. An open parentheses and a closed parentheses. These are essentially the indicator that says, hey, there would be a parameter here if I had one, but I don't, so don't worry about it. You have to include that as a part of creating a function type that has no parameters. Now, let's look at it when there's no return. It's basically the reverse. So you can, when you have a return type, put open parenthesis, close parentheses, just an empty parentheses block, and that is a void return, so your closure does not return anything. All right. So next we're going to look at trailing closures. This is a very specific piece of Swift syntax shortcuts that makes some Swift code very, very, very nice. And when you find yourself frequently using and passing closures to functions, which you will eventually, it makes your code very easy to read in comparison and a lot less cluttered. So let's take a look at a specific case. Let's say you write a function that helps you go to warp speed, and you can pass in the warp speed, and you can also pass in the catchphrase that your captain uses when they tell your ship to go to warp. In this case, when we call go to warp, we pass in speed 9, and we also pass in a closure that prints the word engage, which is how Captain Picard would say go to warp. So what is this all here, right? So basically, for our function go to warp, we take in an int for our first parameter. For our second parameter, we omit the argument name. This is important for trailing closures. If you want to have a trailing closure, you have to omit your argument label. Then we provide the parameter name. This is how within the function you're going to call the closure. Then you provide your your function type for the closure. In this case, this closure doesn't take in any parameters and it doesn't return anything. It's just doing a print execution. It's just doing something within the function, and you don't have to worry about passing anything or getting anything back. So then, when we call go to warp, rather than putting after the 9 a comma and then putting the closure directly in there and then having to close everything with a parentheses again, we can just place the closure after a closed parentheses. This only works if the final variable for your function is a closure. Sorry, the final parameter of your function is a closure. All right. So now capturing values. We talked about this a little bit before. So let's say that we have a function that we call getFelixPrinter. It doesn't take in any parameters, but it creates a closure. it creates a anonymous function. It creates one that has no parameters and no return, so it's just going to execute and do its thing. So within our function getFelixPrinter, we have this cat constant. The cat is a string. It is a string whose contents are Felix. This cat constant falls out of scope once we get outside of this red box. Once we reach this kind of final bracket here, cat falls out of scope. It is released from memory. No one needs it anymore. However, because we have a closure here and a new scope defined, but it's specifically a closure scope, a closure can do something called capturing a variable or a constant, where if a variable or a constant from outside of its scope falls into it, and then within your closure scope you refer to that constant or variable, it is retained within memory as long as your closure is retained within memory, even if otherwise that constant or variable would have fallen out of scope. So here we create a constant called printer. We're passing the closure to this, so this printer has a type of, it has a function type that is a no parameters, no return function type. And we call it as if it's a function, not passing any parameters because it doesn't have any, not assigning it to anything because it has no return. However, it does execute code within it, and in this case, it is executing this closure that prints the cat keyword. Normally, by this point in time, if we didn't have that closure in there, the cat constant wouldn't exist. The memory would be gone. It would have been erased, overridden, because it fell out of scope. But because we have this closure, it's captured and held onto and kept in memory. All right, so that was functions and closures, everyone. We're going to do a 10-minute break now. I don't know what I did. There we go. Nice, starting that. Snack, bathroom, whatever you need to do. So, cool. And questions, feel free to come ask me. Yeah. Boop, boop, boop.